Hello, good morning, and welcome to UCD Research, where I'm Emma Ryan, and we are here for the launch of UCD Sequest. It's going to be a packed morning. We have a lot of people we're going to be talking with across the schedule today over the next hour and a half. But first of all, it's my great pleasure to welcome Professor Orla Feely. He's a Vice President for Research, Innovation and Impact here at UCD.
Thanks, Emmett, and it is indeed a packed and really interesting schedule, so I'll be very brief here. First of all, to welcome everybody here today. This is a really important and exciting moment for us in UCD with the launch of Sequest. Quantum engineering, science and technology are areas of huge opportunity and huge importance, and we really want to bring the best of our minds to bear on the problems associated with this rapidly developing area. So the Centre is a really important vehicle for us in this regard, to enable us to collaborate internally, but also to reach out externally. And you'll be getting a flavour of that today. I'm delighted that we have our leading academics in the space here today to tell you a bit about what's going on. You'll hear also from our funders, our national and of course European and other international funders are really mobilising behind this space. And we've had very important support from Science Foundation Ireland, from Enterprise Ireland through the Disruptive Technologies Innovation Fund, and also the venture funding of the University Bridge Fund, which has supported a very, very exciting startup in the space that you're going to be hearing about. Industry partnership is also really important to us here, and I'm delighted that Dr. Roy Zhu of IBM Research, who are outstanding partners for us in this area, she'll be here to tell you about how we are working together. And of course, academic partnerships are also key, and we have representation from Queen's University Belfast to tell us about how we are going to be working together. So again, a really exciting journey. This is an important phase of that journey, and I greatly look forward to supporting the success of Sequest. Apart from the academics who've worked so hard on this, I want to call out a couple of people in particular from my own team in UCD Research, Colin McMahon and Kevin Murphy, who've worked very, very hard on the establishment of the Centre and to support our activity in this space. So thanks all for what you've done to get us to where we are now. I look forward to a really exciting and valuable journey together, and we in UCD Research and Innovation will support you every step of the way.
Professor Feely for that introduction. And it's now my great pleasure to be joined by Dr. Andrew Mitchell. He is a theoretical physicist here at UCD, and you are, of course, the director of the new Centre for Quantum Engineering, Science and Technology, or Sequest, as we're calling it, because it's a lot easier to say than that mouthful. So, Andrew, obviously there's a lot in that title, like we were saying, and I think a good place to start. And because, as you know, I'm not really a scientist. I write a lot about scientists, I write a lot about engineers. But what is quantum technology, and why should we care about it?
Thanks, Emmett. Well, it's really exciting to be here also at the Sequest launch. Yeah, that's a great question. So, I mean, as you might know, the behavior of the world on the smallest length scales is actually rather different from that of our everyday experience. So when we're talking about the nanoscale world of atoms and electrons, the physics is described by the laws of quantum mechanics, and then things can get pretty weird. So one of the examples of this is that things we might conventionally regard as particles, like the electrons that constitute an electrical current in a circuit, can actually behave like waves in quantum mechanics. And just as water waves in your bathtub can diffract and interfere with each other, so too can the electrons in a nanoelectronic circuit diffract and quantum interfere. So the new property here of quantum mechanics is really this concept of entanglement. It means that a quantum state, if you like, is a superposition or a sort of simultaneous combination of different classical states.
Classical states, and that's one of the few words I actually get, so that's like Schrodinger's cat, right?
Well, so the idea here in fact is with these superpositions of states, that it's sort of a combination of both of these things. This is the sort of true state of matter when it's undisturbed and unobserved. But when you make a measurement of a quantum system, then you see one of these classical states, but with a probability that's determined by the structure of the quantum state. So this is the Schrodinger's cat thought experiment. If you have a box with a cat inside, and you have no access to the information as to whether or not the cat is living or dead, then in a quantum sense, it's kind of in a combination of both living and dead. Only when you open the box do you see one or the other, you see a classical state.
Now, I'm going to ask you for some examples here, because even when you mentioned quantum entanglement, my first thought was how I am when I'm sort of in the middle of the doing, but not quite when I'm trying to get up in the morning. So maybe there are more helpful examples than what I just said that you can give that actually make more sense to people.
Well, so the idea of quantum technologies is that all of this physics is new. It's different from classical physics. The physics of the quantum realm is really very different from that of our everyday experience. The idea of quantum technologies is to use these differences. We want to use this new physics as a resource to do something useful, to do something that classical technologies can't do. So an example could be in metrology. You can leverage quantum effects to make extremely accurate and sensitive sensors of temperature or electromagnetic fields or something like this. But probably the most famous application is that of quantum computation, where we can leverage the quantum entanglement effects to actually use it as a computational resource to do new things.
Now, I always try and make these things as simple as possible because my job, my main role really is to explain extremely complex stuff to people who don't understand it. So that's one of the things I sort of like to go with. I always say, don't explain to me, explain to my dad who's 86. So one of the things I know what quantum mechanics is, well, quantum science in general really is, we use a really, really, really powerful microscope. You can see everything's made of these sort of quantum building blocks, the atoms, electrons, and everything, right? And I'm roughly along the right way there.
That's right.
So is there existing technology already in some way quantum when you get down to it, or is there a lot new here?
No, I mean, that's exactly right. I mean, we do live in a quantum universe, whether it seems that way or not. Actually, a lot of existing technologies, traditional technologies, are using quantum effects, whether we realize it or not. In the 1940s, they developed the transistor, for example. This is relying on the quantum properties of semiconductors, and now, of course, they ubiquitously appear in the computer microchip. In the 1960s, we developed the laser. This is used in your DVD player. In the 1980s, we discovered high-temperature superconductors, which are used in medical diagnostics or maglev trains, this kind of thing. So all of these technologies, which we regard by now as traditional technologies, are using these quantum effects. But I guess the new thing here now is that instead of just using the sort of intrinsic quantum properties of naturally existing materials, we're now in a position where we can engineer quantum states of matter in the lab, in our technologies. We can manipulate them, and we can control them, and we can use this now as a resource to do new things.
Okay, that's really fascinating. But one thing that's sticking out to me here is a lot of this refer to some pretty old stuff. Like I'm 40, I'm pretty old, and like I feel it as well in my bones when I go up. But quantum theory is older than me. It's been around since the 1920s. Like we think about like sort of the Great Depression. We've had a World War. We've had all sorts of stuff since then. So why has it taken like 100 years to put the theory into action? Like, why is now the time when we're seeing this sudden flurry of interest?
Yeah, I mean, that's a good point. I mean, quantum theory has been around for 100 years, as you say, basically. I mean, developing new quantum technologies that can really do stuff for us is just a huge challenge, and it really has taken 100 years to get to this sort of breakthrough point that we're at now. So one of the things that's been developing over the years, of course, is the incredible miniaturization of electronics. So in the industrial nanofabrication techniques now, we can cram billions of transistors onto a single microchip. The feature size is really down to the nanoscale of a few nanometers. So this is a technology that's been able to access the nanoscale. It's taken a long time.
And I've got to cut across you there because I love it when you're referring to the nanoscale nanometers, because that's one where it's so small, even conceiving it with your eyes, and not even actually seeing it, conceiving with your mind. It's just impossible to even conceive mentally. Like it does require this level of technology to really conceive it. Like.
Exactly, and it's amazing the technological advances that have been made to really get us down to the nanoscale. This has taken a long time to develop. Alongside this, we have tools to characterize and visualize quantum matter. So the scanning tunneling microscope, for example, can really visualize things on the nanoscale and indeed manipulate them. And sort of alongside this, we have the sort of theory and simulation of quantum devices. We really need this to understand what's going on in these systems, and also for rational design of new systems. And now we also have the entirely new field of quantum algorithms. This is computer science on quantum hardware. So all of these things have separately taken quite a long time to develop. The exciting thing now, I think, is really that we're in a position to bring all of this together.
And so one of the things that jumped out to me is, because of my job, I edit Connected Technology magazine and Business Post. It's one of the natural areas I hear a lot about from many of the experts we're talking to in it. Comes up quite a lot, and to my shame, they still have trouble explaining white matters to people, let alone people who are very smart, and, well, people who are very scientifically smart. They remind my dad who's more a different kind of smart, because I want to say my dad isn't smart on a live broadcast. But so explaining why it's important to even sort of the more research-driven people, and also to my dad, like, why is it important? Because it sounds to basic, person, it's just faster computers, but there's a lot more to it than that, isn't there?
I guess the point is that quantum technologies have the potential, sort of game-changing, transformative potential to do totally different kinds of things, solve some of the hardest problems. I mean, that we have potential applications, I should say, from some sort of material science and drug discovery to finance and cybersecurity. I mean, there's just so many different applications, for example, of quantum computation. When you mentioned this idea, is it just faster computers? I mean, not necessarily. I mean,
like, it is more than speed. Like, it's what it's doing with the speed, really.
Exactly. I mean, we've seen over the last years and decades, an incredible increase in computing power from just standard computers. And one of the big drivers for that, one of the things that's really allowed that to happen, and we see Moore's law and so on, this exponential increase. One of the things that's driving that is the miniaturization of the electronics, as I mentioned, the sort of getting the transistors down to smaller and smaller sizes. But we're really down to the nanoscale already now. I mean, the transistors in these microchips are literally a few nanometers across, and they've basically got as small as they're going to get. Maybe there's a little bit of wiggle room, but we're already on the nanoscale. In fact, there are sort of quantum effects at low temperatures observable in these chips already, and we'll probably hear something more about that from one of our industrial representatives later. But sort of the point is that these classical technologies are sort of getting to the limit.
And you're spot on, because I remember I was at a factory of a well-known Chinese phone maker. We'll leave that aside as which one, a couple of years ago. And they were just showing sort of a sample floor of how they apply some of what you're describing there. And it's such a small scale that they have to print it on, because even like with robotics, standard, assembly just won't work. It has to be printed into the hardware, so to speak, is the process, because we are describing that size. But everything you're describing to me here, it's like, you mentioned the problems it's solving. If we're talking about problems in this day and age, the environment's kind of a big one. It's I've got no kids, so I'll be fine. But there's a lot of people tuning in who I'm sure would like the next generation to have a good life. And am I right in saying that right now, when it comes to developing even a single neural network and machine learning, you're talking about the similar level of like sort of environmental impact to like an average car's lifetime? Like, that's an awful lot. Like, so can quantum help address this?
Yeah, I mean, that's exactly right. There are huge pressures. I mean, as we've seen, this development of standard computing resources has increased. It's kind of reaching its limit, but our desire for ever more, computationally hungry technologies is not reducing. With these machine learning applications and so on, these are incredibly computationally demanding these days. That's a really big business. And as you say, it's not just costly in money, it's costly in terms of the energy requirements and toll on the environment. So we do need something different. And I think that thing is quantum computers and to exploit quantum technologies. So we want to use these quantum effects, quantum entanglement as a resource to do quantum computation. And the quantum effects can also provide a route to doing this in a much more energy efficient way as well. Okay,
that's really, really good. Now, I'm also an alumnus of this wonderful institution, which has had so many new buildings as they left. It's almost like trying to say, we didn't really like you, so we made it nicer after you went. Don't worry, UCD loves me. But the now is, I think, a key thing with UCD. What's special about this being the place for the centre, and why are we launching this centre here and now? Because obviously there's a lot of moves in Europe. There's the Euro QCI. I'm guessing that's obviously a factor. But like, why else are we thinking here now? UCD is the place to do it, and this is why we're doing it.
I mean, there is a long history actually of quantum science in UCD, going right back to some of the early days of fundamental physics that was done here. But now we don't just have physicists working on quantum, we have mathematicians, we have computer scientists, we have engineers, all working on different aspects of quantum. And in the last few years, to answer your question of why now, in the last few years, we've been hiring lots of new staff in quantum, also through the Ad Astra Fellowship Scheme of UCD, really recruiting to get more and more people into this priority area. So now we really have this sort of critical mass of researchers, but they're not just physicists, they're in all sorts of different fields. And we actually now have 24 members of academic staff, permanent full-time academic staff working on aspects of quantum who are full members of Sequest. They're in the 4 founding schools of physics, maths, engineering, and computer science. So we see that there's this sort of plurality of different fields coming into the study of quantum now. We've finally got this critical mass, and so now is a good time to launch this centre.
And it must be fascinating for you working with this cross-disciplinary group, because always in academia, like my background's commerce, but even there was cross-disciplinary work, which I found quite fascinating. With the sciences and engineering, it must be for you as a personal project quite intriguing.
Yeah, I mean, this is the key aspect of the quantum centre that we have here at UCD. I mean, it's a recognition that the complexity of these challenges requires a collaborative approach. I mean, we'll probably see that the relevance of quantum will even spread to other disciplines beyond the traditional ones that I mentioned. This collaborative approach of bringing in all of this different but complementary expertise, experience from all of these people in different schools is absolutely crucial. So that's really what we're after here.
Now, one thing I touched on there before we move on to the next question was the Euro QCI Ireland's signed on, so it's going forward. For those who aren't aware, but tell us a bit about what's going to be happening there.
So there's been a lot of initiatives in Ireland, but also in Europe and worldwide in quantum. So we see the EU quantum flagship that's investing €1 billion in quantum science and technology. It's just a huge investment, and that's with good reason. It's because quantum technologies hold so much promise. As you mentioned, there is also this quantum communications infrastructure, which was actually just announced this morning. That
breaking news.
Breaking news.
That's launch.
So all of the EU member states have now signed up to this, and this is a commitment that we'll try to develop this quantum communications infrastructure. And in fact, UCD has a bid in for developing part of this network.
That's fantastic. Now, you mentioned UCD, and you've mentioned all the interest in quantum. I mentioned my magazine earlier, and I'm always being asked to write about it, but it's not usually to do with academic institutions, it's usually to do with very, very large tech companies. The city alone, never mind the wider country in Europe and the world at large, is loaded with tech giants in their presence doing work on this. So is this centre trying to compete with them, or is it trying to collaborate with them? What's the approach here?
Well, we're certainly not trying to compete with the big tech giants, we're trying to work with them. I mean, it's sort of very important that we take this collaborative approach that I mentioned, and certainly the industry has a lot to offer. We've seen, as I mentioned earlier, with developments of miniaturization of electronics and so on. This is actually driven from the industry perspective. So we want to work with the tech companies. We actually have representatives from IBM and Google and Equal One Labs on our advisory board for this reason. We want to be able to see what the tech companies want, what the industry needs, from where quantum technologies are headed from a sort of commercialization perspective. So we definitely want to work with these people.
And I will say the presence of all those tech giants has improved the quality of coffee in this city, no doubt. Now, when it comes to the centre, beyond actually having more great coffee in Dublin, what are the fundamental goals? Like, what do you want to achieve leading this centre?
I mean, one of the most important things, I guess, is to promote quantum science, engineering and technology in Ireland. And although our own activities here in Sequest are naturally based in UCD, as Ireland's largest university, and now with this critical mass of researchers in different aspects of quantum, we feel that we can sort of facilitate the national debate around quantum. I think it's also really important that we have an all-Ireland approach to this, taking into account all of the different universities here, and also the north-south dimension. It's very important. We have the head of maths and physics from Queen's University Belfast on our advisory board as well, for this reason. So that's part of it. I think in terms of our activities here in UCD, the key point is to foster these collaborations between different researchers, between researchers in different schools. As I mentioned, our 4 founding schools of physics, maths, computer science and engineering. These researchers in these groups have been incredibly successful in doing the work that they've been doing. But now with Sequest, we're starting to see more and more of these collaborations between researchers in different schools, breaking down these old disciplinary boundaries. So that's really what we want to achieve here in Sequest.
I just want to ask you one last thing. So you mentioned the 4 founding schools. There are also 4 thematic pillars. So if you could just briefly tell us about those before we get on to our next guest.
Yes, so we've sort of built Sequest around our areas of expertise, naturally. And one of these is in quantum devices and all that entails. One is quantum computation, one is quantum information simulation, and the final one is quantum literacy. Of course, as a university, one of our goals, of course, is to educate. And I think with Sequest, because we have all of these different contributions from people working in different related complementary fields, I think this is something that we can really get a unique perspective on. So I guess maybe we should...
Yeah, I was going to say, Andrew, that's been fantastic, and that's really been fascinating. I feel slightly smarter than when I started asking these questions after that. But now is a great time to start hearing from our 4 champions. And first of all, we have Steve Campbell from the UCD School of Physics, who is the thematic champion for quantum devices.
Hi, I'm Steve Campbell. I'm an assistant professor in the School of Physics, and I want to tell you a little bit about one of the major research themes that we're developing in the center, which is related to quantum devices. Now, you may not realize it, but we already live in a pretty quantum world. So the fact that energy comes in discrete packets and that energy levels themselves exist, this is the underlying principle that gave us things like lasers, semiconductors, transistors. So today's computers, for instance, they operate on quantum principles. But what's happened over the last number of decades with great advances in the experimental control of right down to the single atom and single photon level is we are moving beyond these quantum enabled technologies into what we call quantum enhanced technologies. And these are things that exploit the more exotic aspects of quantum mechanics, things like superposition and entanglement, in order to realize technologies that either outperform today's devices or perform tasks that would be otherwise impossible. So you'll hear a little bit more from my colleagues about quantum computers and quantum crypto systems, but quantum devices kind of is a little bit more all-encompassing. So it also involves things like quantum components. So let's say quantum analogs of transistors, but also storage devices, things like quantum batteries. And then one area in which I think that quantum technologies are going to have a huge impact in the next couple of years is in this realm of quantum sensing. So thanks to Heisenberg's famous uncertainty principle, quantum mechanics actually sets the fundamental limits on how accurately we can measure any quantity. And what this means is that our best clocks, our best thermometers, they're all going to be based on quantum mechanical systems. So within the center, we have really a wonderfully diverse range of expertise to draw on. And what we're looking to do is to leverage that in order to make the most and to find a roadmap towards these quantum devices. So there's a few obvious questions that we need to address. So for instance, we want a device to do what it's supposed to do, and quantum mechanics and quantum systems are inherently fragile. So we need to develop schemes in order to coherently control them. We also need to understand how, when we scale down to the nanoscale, how the physics, the fundamental physics starts changing. And we also need to find ways in which these devices are efficient, that we need to understand the resource consumption, how much energy that is needed. Addressing these kind of different strands together, this is then going to give us a roadmap towards realizing quantum devices that are effective, efficient, and scalable, and allowing us to really exploit them to their full potential.
Hello, my name is Elena Blakena, and I represent the School of Electrical and Electronic Engineering. I would like to introduce the research theme of quantum computation. Computation systems based on key quantum mechanical properties of superposition and entanglement are known as quantum computers. They operate using qubits, elementary units of information in quantum information theory. The concept of the quantum computer originated from an idea that in order to efficiently simulate one quantum system, another quantum system should be used rather than a classic computer. Quantum computation is not limited to simulations of quantum systems. In principle, it can be used for any physical process. At the core of quantum computation is the synergy between the physical implementation of qubits and quantum algorithms. Operational quantum computers exist, and the progress in this field has been actually reported in recent years. The superconduction qubit technology seems to be dominating at the present, but many other qubit implementations are available. Photonic systems, trapped ions, and semiconductor quantum dots are also recognized as possible options to implement quantum processors. In fact, these technologies are not necessarily competing. Perhaps quantum computers in the future will be specialized for different tasks and will be built using different physical implementations of qubits. Quantum computers do not work with the classic computational algorithms we know and use today in classic computers. They require a special class of algorithms. For some quantum algorithms, such as the famous Shor's integer factorization algorithm or quantum Fourier transform, it has been proven that they have potential to outperform their classic counterparts. At the moment, many algorithms and applications for quantum computing have been proposed and tested in available quantum simulation frameworks. Some of them even can be tried in existing quantum computers. The current generation of quantum computers is often called noisy intermediate scale quantum, since we are not quite there yet to fully leverage the advantage of quantum computation. However, even now, there are many applications in quantum chemistry, material science, and machine learning to be excited about. Quantum computation is a very challenging task for physicists, engineers, and computer scientists. It requires to connect algorithms with hardware and to understand what physical signals we send to quantum devices and how we interpret them for meaningful results. Thank you.
My name is Rupert Levine from the UCD School of Mathematics and Statistics, and I would like to say a few words about the quantum information and simulation theme. First, quantum information. So quantum mechanics allows us to store, manipulate, and transmit information using quantum systems and exploit their many exciting properties. So a key challenge is to do that without losing information to decoherence and other noisy effects. So one problem, which falls squarely under quantum information, is that of encoding information in quantum systems, ideally so that the information is immune to the effects of noise and other decoherence effects. For example, two promising approaches here include quantum error correction and topological quantum computing. So associated with encoding to protect from noise, you also have encoding to protect from eavesdroppers. So this is the idea of quantum security and quantum cryptography. And in fact, quantum mechanics allows some exciting new opportunities here which come with guarantees of security. Now onto the problem of sending quantum information. So suppose you want to send some information encoded in some qubits all the way across Europe. Well, you might not be able to do that in one shot. So because of that, it becomes important to try to build quantum networks and work towards the quantum internet. And this also comes with some challenges unique to quantum information, because simply copying quantum data becomes problematic. So quantum information, I guess, is exciting because we have these new resources at our disposal when we encode information in quantum systems, in particular, entanglement and superposition. On the other hand, it's slightly less clear exactly how far these new capabilities can take us. So it becomes important and interesting to figure out exactly what they can and cannot do. So this is another active research topic. So allied with the limits of quantum computation is the idea of post-quantum cryptography. So we know that quantum computation can break the existing cryptographic protocols that we use in devices all around us, but what can't it do? So the idea of post-quantum cryptography is to devise protocols for securing data which can't be broken by quantum computers. So that's also exceedingly important for the future. So the second strand of this theme is simulation of quantum systems. So you could say that the first nuggets of the idea of quantum computing started here with the idea that a quantum device should be able to simulate a quantum system more efficiently than a classical device can. So this is the idea of quantum simulation of quantum systems. On the other hand, it still remains an important and interesting problem to try to improve our simulations of quantum systems using classical devices.
Hello, my name is Dr. Simon Caton. I'm a member of faculty at UCD's School of Computer Science, and I'm here to present Sequest's vision for quantum literacy. As it stands, Sequest is a collaboration of 4 schools at UCD. However, the quantum landscape spans many other domains, and herein lies a very fundamental challenge for anybody who wants to enter the quantum space. They need to have knowledge and expertise in more than just one area, and this can be quite intimidating, especially when we start to think about some scientific domains do not even yet know what their quantum application is or what their future relationship with quantum technologies will be. If we think about some of the most fundamental building blocks of quantum technology, from how we represent data to some of the core underpinning theory to how we program quantum computers, each of these things can be quite scary and intimidating because they are unfamiliar. And this can become more and more complicated dependent upon how advanced our own expertise is in specific areas that underpin quantum technologies. The challenge that we face here is that we can find it very difficult to differentiate fact from fiction, and we've seen this in other domains as well. Thus, at Sequest, our goal is to try and create a suite of programs that can help cater for different types of students, from school children who have fundamentally different needs to students, postgraduate students, researchers, academics who have fundamentally different needs to journalists who have to try and explain to the world what the advances in quantum are, what they mean, and what their implications are. And similarly, we have politicians, scientific funding agencies, businesses, and thought leaders that also have to try and disentangle what quantum means for them, as well as the future of the decisions that they are trying to make. And when we talk about quantum literacy at Sequest, what we mean is providing this set of tools, programs, and educational platforms that allow people to start their quantum journey from the very beginner through to intermediate and through to a more advanced, perhaps even university or even further levels of education. And here, the ultimate goal is to try and create a more quantum literate workforce capable of differentiating between media hype and scientific reality.
And welcome back, and thanks to all 4 of our champions for their speeches there. Now, before we get on to our next bit, one bit for all of you watching at home or wherever you're watching is we'll have a Q&A section a bit later in this session. So if you've got any questions, get them in now through the Q&A section you can see there on the presentation, and we'll answer as many as possible at the end of today's session. But this isn't denial, and Sequest isn't acting on its own. What the work UCD does is part of wider and international affairs. So with that in mind, we have a video now from the EU Quantum Flagship Initiative, which embodies the EU's vision for strategic research and is quite fascinating in terms of the amount of work it's doing across Europe. that video from the EU. Now, UCD isn't doing this on its own. There are many funders who are supporting it, and we're going to hear perspectives from each of them now. First of all, it's Dr. Kieran Shoga, who's the Deputy Director General at SFI.
Hello, can you hear me okay? I'm going to assume the answer is yes to that. So thank you for the invitation to join you here today. And firstly, let me just say congratulations to everybody on the launch of Sequest. And I'm delighted as well that there is a name like Sequest to work with, because many of these quantum centers, they do have rather challenging names. So Sequest is quite catchy. But and I also recognize just how much work and effort goes into launching and having something like this in place. So that is it's congratulations to everybody involved. I heard the earlier conversation as well, and it's always fascinating to hear the conversation people have around quantum, and that the fireside chat led by Emmett there was fascinating. One really good example, by the way, just that I've heard in the past, of how to explain nanoscale, which is often the challenge when we're talking quantum. How do we explain that nanoscale? How do we explain quantum? Anyway, it is important that we are able to communicate this. But a really good example of nanoscale that I heard from colleagues in the past was that it's about how far your fingernail grows in 1 second. So it just gives you an idea of the scales we can be operating on. So to reflect from a funder's perspective, the importance of quantum technology and what that means in Ireland. It is undoubtedly an emerging technology, and it has potentially, it's going to be very disruptive. And it can disrupt a very wide range of areas. You know, sometimes people think of quantum technology or quantum computers in particular, and they think, you know, this is going to be faster computers. So, you know, my Microsoft Word and PowerPoint is going to run faster. And really, that's not what this is about. The areas of disruption are much broader than that. Quantum technologies is not about faster computers. It's about tackling different or existing problems in new ways, which allow us to use the power of quantum computers. And what we're seeing is industry really does get this. They have understood the power of and the potential. And it's a power and potential that ranges across a range of industries too. So there are obvious ones such as the pharmaceutical industry or those involved in materials science and materials research. But there's other areas, fintech and climate, and other areas where people, energy, etc., health. There's a wide range of areas where people are seeing that the power of quantum computers could impact this. And depending on the reports one reads, the time scale varies. It's hard to predict with a disruptive technology exactly how long it's going to be before we really need to be good at this. But it does range from some reports saying, you know, 2 to 5 years before there's quantum advantage for different companies, to others saying 5 to 10. That is a little bit in flux. And exactly which technologies and which areas, is it sensing, is it communications, is it computing, which areas take over and have the greatest impact first, is yet to be determined. But what is not unclear, and what we are absolutely adamant on, is the need for the skills, the talent and skills. And by talent, it's the researchers, it's the academics, it's the people coming together, the people here on this launch today. That talented, skilled group, that is what is going to attract industry players. That's what is going to attract the best other researchers and the best PhD students to be in Ireland, to want to be close to that locus of new ideas. And hence, centres like this are quite important. You know, when I reflect a little bit on the current status in Ireland, I'll be slightly provocative in my views on this. You know, when we talk about quantum technology and Ireland and where we rate, and when we compare ourselves to major international countries, there's no doubt major international countries, they are investing heavily in this. We're talking millions and sometimes billions in the level of investment. And while we have pockets of quantum excellence in different fields and different locations, I would probably describe us as at that point of being nearly good. We're not at that world scale. We're not using the full capability of what we can be. But we do have those pockets of excellence. We do have teams in different fields and different locations who are world leaders. And there is a job and an onus on those of us in that funding sphere to see how we can bring that together to support it, to provide the funding for it, to advocate for it as well, advocate for Ireland to invest in this space. And that is something that we see as part of our job as well. We're nearly good, we can be really good on this world stage. And we are seeing some convergence, some clustering happening in Ireland, which is a very positive development. And an important part of today's thing is we see those natural leaders, those people who come to the fore, who grab this and say, I am going to make something happen. And again, I really want to congratulate the team involved in this, because that's important. It's those leaders that come out in Ireland that say, we're going to make Ireland a great place for quantum. We recently established, and when I say recently, just prior to the pandemic, a national advisory forum on quantum. And the idea was to get industry and academia and policymakers into a room together and say, right, what are we going to do about quantum? And that is our advantage, our tactical and strategic advantage in this country. We are maybe small and don't have the big budgets, but we are interconnected. And we need to use that interconnectedness in order to create that ability to have the whole greater than the sum of the parts, and to be able to do things, to be agile and responsive in ways that the big countries with the big budgets perhaps can't do to the same extent. It's also good to see that we are collaborating internationally, that we are building our profile. And I was delighted to see as well that we signed up to EuroQCI, so the quantum communications infrastructure. It's an important step. It also signals very clearly that quantum is important to us in Ireland. But we do need to go further as funders. We do need to be doing more in this space. And there is more we can be doing. We could be more proactive in this space, and to be a bit self-critical, there's more areas where we could fund in quantum. We have some exceptions like Quantira, which is underway at the moment. And it's great to see the interest in that, but we need to do more there. So what next, and where to from a funder's perspective? Well, I know there is a national strategy underway in terms of a national quantum strategy. And there's a team working on this, which is those experts around the country talking amongst themselves about what is the national strategy, and a white paper will come from that. It'll be important to identify those gaps that are in the system currently from a quantum perspective: skills, talent, infrastructure. What do we need in order to be world leaders in this space, to really make our name known? And how we, the strategy can help us to exploit that agile and interconnected nature of the small size of Ireland. We need to continue to build our international collaborations, and we need to be really good at engaging with industry much more effectively, about collaborating early on in early stage research, as well as recognizing the translation opportunities that come. From a funding perspective, we need to explore new models and new opportunities for funding. We need to be thinking of things such as quantum proto centers and other centers, individual research programs, European programs, collaboration programs. And that is something that we are working on at the moment. I would encourage as well that we are looking at how we all input into the future of Irish research. So Irish government is working on the successor to Innovation 2020, which is the existing strategy for research and innovation in Ireland. And that successor is being replaced at the moment, and there are public consultations and engagements with academics and other stakeholders to say what should be in that strategy. And having that very proactive, forward-looking view of grabbing those new technologies, being able to take that first mover advantage in new and emerging fields and not be that fast follower. Take those first mover advantages in things like quantum and be really good at that. So we can input into that and show that that's an area that we as a country want to go. So I know you not to talk too long about this. So today's launch is important. It shows that leadership. It pulls that cohort of researchers together. As a funder, we are very keen to support this emerging area of research and to do more and to continue the dialogue. And all I can say is I wish you all the best with it. And I really look forward, hopefully, to getting to meet you guys in person sometime. Thank you very much.
And thank you, Kieran, for those words. Our next speaker is Dr. Imelda Malamkin. She's the manager of the Disruptive in Technology Innovation Fund, the DTIF as it's better known, at Enterprise Ireland. And Imelda, thank you for joining us.
Thanks a million, and good morning all. I suppose I should start by congratulating the team on the launch of the centre. It's a fantastic achievement. And then coming straight to the perspective of the Disruptive Technologies Innovation Fund, our experience really has been the funding of the first quantum computing in Ireland project. And really that was to explore the potential of quantum technologies to address challenges. And that's in areas like financial services, logistics, drug discovery. And I think the timing of DTIF was great in that it was bringing together what was a previously fragmented activity. So it had just the kind of collaboration that we're eager to support, IBM leading the project, research teams coming from several research performing organisations in Ireland, so UCD with Tyndall, with NUI Maynooth, coming together on a shared agenda, which is exactly what we want. Working with high-tech companies like Equal One Laboratories and Rockley Photonics, and actually even an application partner in MasterCard. So with the DTIF activity, this was just over 7 million euros of the fund in an 11 million euros initiative. And of course, that's a key activity within DTIF is the mobilization of private funding. So fantastic for an area like quantum. In terms of what we see enabled by a project like that, really it's the recruitment of very strong teams with some substantial materials and capital equipment in the research performing organisations and actually in the small companies as well. So Based on that experience, we're watching the progress of that project, that program of activity with interest. We're watching it as a key ecosystem enabler, and really we're watching the potential to drive employment based on quantum technologies in the longer term. So turning then to DTIF and where are we going with the fund? I guess the fund is maturing. We've seen some interesting developments in that the fund has mobilized companies, the research community to compete for funding. And a point that we're often making at the moment, it's the first time that companies have competed for funding at national level. And so for us, it's very interesting that they can do it, and that in a community like your own, you can fit the quantum agenda with the fund, our needs with yours to really make it work and to seed the activity, the type of activity that leads to the generation of research centres like today. We've funded more than 235 million euros of funding across the projects to date, and they span everything from life sciences, medtech, AI, through to energy, sustainability, and of course, quantum technologies. So our messages for today, really, that's a very large DTIF portfolio. Can you mine it? Can you mine it for partners? Can you mine it for challenges that you might look to address with quantum technologies that you're developing? The portfolio is full of collaborative teams, small companies that are bright sparks in the Irish landscape, working with companies like IBM, for example. So really, can they provide an opening to those challenges for you? We'd be very happy to make the links for you. Many of the projects are actually led by research-intensive SMEs, and actually we've seen some of our first examples of small medium enterprises that participated in other projects now coming in to lead GTIF projects, GTIF applications. And a key question for us would be, can you work with the companies to facilitate that? I think you have a really interesting team of people within the centre where actually I'm sure that you can do that. And of course, as mentioned by several of the speakers already, we'd love to see that the DTIF facilitates the building of the team locally, which essentially can be a great starting point for competing globally. So whether that's competing for other funding sources globally, or whether it's companies looking to compete out there in global markets, we think that we can seed that activity very nicely through DTIF. So we'd love to see your next generation of DTIF applications. We're waiting for them. We'd love to see more quantum technologies within the mix. A reminder that it's an opportunity for innovation at scale, a real high point being the fact that it's collaborative. And again, several of the speakers have really made that point that collaboration across sectors, across research areas is key within quantum. And that's where we see the real novelty in the DTIF projects. The projects must be the sum of all parts. And now you have the centre as the nucleus of that activity. So from our side, we're working on the next DTIF call. We're hoping to launch later this year, and we'd love to see you using it. Thank you very much.
And thank you, Imelda, for joining us. Our last funder perspective now is from Dr. Helen McBreen, who is a partner at Atlantic Bridge.
Good morning, everybody, and thank you for the invitation to speak this morning. So we've heard this morning that quantum computing is the future for organizations looking to use large amounts of data, AI, machine learning to accelerate real-time business intelligence and innovative product development. And quantum computing has certainly progressed from a research experiment now to a technology that's certainly on the brink of transforming key sectors, including, and very importantly, sectors like medicine, cybersecurity, and aspects now of climate change. And as investors, we track this market very closely, and it is estimated to be projected to be worth over 100 billion in the next decade. Investments in quantum computing continues to increase, And these investments are really being driven by organizations, as we've heard about, seeking to achieve a competitive advantage by using quantum technology to improve and accelerate their business processes with enhanced AI capabilities, better security, and more optimized algorithms. But quantum is still, as we've heard, at an early stage. However, significant technology achievements are continuing to happen. And this is certainly evident in the number of European startups and early stage companies continuing to engage and collaborate on quantum projects. And all the while, this is working to develop a very vibrant European quantum computing ecosystem. And this growth provides access to quantum computing hardware and software, the necessary talent, and quantum business collaborators. However, complex technologies, limited skill sets, lack of resources and costs, they can all be really terrible limiting factors. So it's vital here in Ireland that we firmly plant this flag for quantum and that we leverage our research resources to thrive in this market. For that, we are really welcoming the launch today of the UCD Quantum Centre. As the primary investor in early stage in research intensive companies emerging from the Irish research institutions across the country, across all sectors, including deep tech, software and life sciences, Atlantic Bridge is fully committed to supporting UCD and this centre, and we look forward to working with all the researchers and partners involved. Since 2016, Atlantic Bridge has raised over 120 million across 2 university venture funds, of which UCD is a key partner. And in addition to these funds, we have over €1 billion in capital under management and connections to global industry partners and capital partners to support the growth of research-intensive companies and build world-class deep tech companies of scale. We're certainly delighted to be the backers of several Irish leading chip companies, including companies like Decawave and Movidius, along with global companies that are developing next-generation AI chips, significant power management innovations, edge computing, and now, of course, quantum. And all of these technologies will support our global technology revolution. We're particularly proud to have backed Ireland's first quantum computing company and UCD spin-out, Equal One, and we're working with the company and partners to bring this disruptive technology to market. Jim Clark at Intel has said that quantum supremacy is perhaps not the ultimate goal here, and the real goal should be about quantum practicality, when quantum computers can actually do something life-changing or something unique. And yes, quantum computers have begun to complete very basic tasks, but researchers are ever inching towards that threshold of quantum computers being able to do something game-changing. And you'll hear shortly how Equal One is on that path. Investors have funded up to 100 quantum computing technologies globally, and many of them are spin-outs, not surprisingly, from university departments. And our universities are often the source of the most disruptive innovations and game-changing technologies. European governments are continuing now to pour money into quantum projects. France has recently pledged just under 2 billion, and Germany have also pledged 2 billion. And much of this is partly motivated by a need to avoid leading academics leaving their regions. And we here in Ireland must do similarly to nurture our brain power and continue to create a thriving quantum computing ecosystem as part of this European approach. So my final words are to say congratulations to UCD and the team at the Quantum Centre on this significant launch today, and we're very much looking forward to next steps.
And thank you very much for those words, Helen. We're now going to get a couple of funder perspectives, and the first is from Dr. Rui Zhu, who was the Director of IBM Research Ireland.
Hi everyone, this is Rui Zhu. I'm the Director of IBM Research Ireland. Today is a very exciting day and a very important day. So our congratulations to UCD for the launch of the Center for Quantum Engineering, Science and Technology. I'd like to take this opportunity to share with you some of the important aspects about quantum technology. So let's begin with why quantum? As you all know that, even though today there are many problems can be addressed by the classical computers, there are still many very hard problems in our society, in science, and in business that cannot be adequately addressed by classical computers. Some of the problems can be potentially tackled by quantum computers, which use fundamentally different algorithms than classical computers. Those algorithms make use of the quantum effects, interference, superposition, entanglements. So based upon the quantum characteristics, we see three potential application areas. First area is in simulating the quantum systems, which can be used for new materials and drug discovery, such as finding a new material to make more efficient and cheaper batteries. Second area is in AI. It can be used for better model training and pattern recognition. Third application area we see is in optimization, such as financial risk modeling and logistic optimization. So all these three areas are very important, not only to the industries, but also academia in Ireland. The second aspect I would like to share with you is the pace of quantum technology development. I'm sure you're all familiar with Moore's law, which predicted that the density of semiconductor chips doubles roughly every 2 years. The semiconductor industry followed that roadmap for decades. So we are now in a new era of the Moore's law. In the last few years or so, IBM has demonstrated that we can double the quantum volume every single year. So in February this year, we published a comprehensive roadmap that covered not only the hardware layer, but algorithms, applications, and services. You're talking about a whole stack. That's not just a roadmap for IBM, it's a roadmap for the quantum industry. So we are not dreaming of a quantum future, we're delivering on the plan to get us there. So I urge you to join us on this very exciting journey. All right, now the last aspect I'd like to address is the development of quantum skills, which is essential to embracing the quantum era and also scaling the quantum ecosystem. Now, finally, we're looking forward to partnering with UCD and also other technology leaders in quantum, not only to develop technology, but also to develop quantum literacy. Thank you all and enjoy the launch event.
And thank you, Dr. Ruiz, for that fantastic industry perspective there. Our other industry perspective is coming now. It's from Jason Lynch. He's the COO at Equal One.
Thank you, Emmett. So as Emmett mentioned, my name is Jason Lynch. I'm COO of Equal One, which is a spin out of UCD. We build quantum computers. I'm going to tell you a little bit about our approach. But first, I wanted to try to give you some sense of the impact of quantum. We've heard at various points today the potential of quantum. What I wanted to try to do is give you an analogy of where I think quantum can get us. And I don't know if you've seen this week on the news, there was talk of the Nokia 3310, and that was released in September 2000. And it very coincidentally is 20 years ago since the iPhone 12 Pro was released in October 2020. And I'd like you to think a little bit about the impact that this has had on our lives in 20 years, right? So, we don't need to, we don't get lost anymore, right? There is, nobody gets lost, ordering an Uber, Airbnb, ordering food. I mean, it's just a tremendous impact on our lives. My contention is that when we look back in 20 years, and I'm happy to make an invite with anybody here to meet in 20 years in 2041, that actually the impact that the last 20 years has had will pale in comparison to what quantum will bring us in 20 years. Quantum is forecast to create €1 trillion of value in less than 20 years. You've heard about the applications. I think, if you think about that number, it's quite remarkable, right? It's 2.5 times our GDP. It's multiple times the size of the cell phone industry today. So really, I believe that quantum is going to change the world. It's a paradigm shift and is going to enable applications that we just can't think of today. So I don't think anybody 20 years ago could imagine what the impact of smartphones has been. But what I'm sure of is that, you know, quantum is going to have a similar and even bigger impact. So I'd like to talk for a minute or two on Equal One. So we're a spin out of UCD. One of our co-founders, Dr. Bogdan Szczeszewski, is a professor and part of Sequest. Our CTO, you heard from earlier, Elena Blakina. Our approach is to try to do quantum on a commercially available silicon process. And our founders have been talking about this for the last 15 years. And when this became available, you heard earlier from Andrew about nanoscale type of geometries here. That's when the company was formed. And what we're trying to do is democratize quantum computing. We make the quantum processor, we design it, we get it fabricated in global foundries in Germany. It sits in cryogenic temperatures. We have a demonstrator product that's running for the last 18 months. We have over 50,000 experiments. I would welcome anybody to visit it in UCD. You've heard also about the applications, in terms of aerodynamics, battery materials, medicine. The opportunities here are huge, and we're excited to partner with Sequest. I think it's a huge, quantum is a paradigm shift. I think this multidisciplinary bringing together of the key disciplines here that we need for quantum is going to accelerate, our ability to make impact in this, and we are hugely excited to be part of it.
Thank you very much for that, Jason. We are now going to move on to a very special guest speaker, because as Andrew mentioned before, this is an all-Ireland project. We are working with Queen's University Belfast as well. So it's my great pleasure to give that academic and all-Ireland perspective from Queen's University Belfast, Professor Mauro Paternostre.
Thank you very much. Thank you very much for this opportunity. I will share my screen and share a few slides that
this is proof we're live, by the way, folks, that Mauro's saying this.
Say it again?
This is proof that we're live, that you're asking this, by the way.
Yeah. Okay, so I hope you can see my screen. Yes?
Yes, we can indeed.
Perfect. Okay, so I was recently asked to provide somehow a view of a vision towards an all-island framework for quantum technologies, and I think this arena is the best possible stage to illustrate it. So I'm Mauro from the School of Mathematics and Physics at Queen's University in Belfast. I'm the head of the school, and I also lead the quantum technology group at Queen's University, which was the first quantum tech group in all Ireland. And I'm incredibly happy that is no longer the only one, and therefore I very much welcome the initiative of funding Sequest, and which is just, in my opinion, is just the latest addition to a growing picture that is getting incredibly exciting. However, I was asked to provide a critical friend view to where Ireland is and where Ireland can go in the development of a framework for quantum technologies. And that's exactly what I'm going to do. So we'll start with the bad news. And the bad news is that there is a gap, an existing gap with major players worldwide. The interest and the investment in quantum technology worldwide is huge. This was mentioned already by Kian, for instance, and is growing. And the numbers are astonishing. And Ireland is not yet there. And is not yet there for a series of reasons. First, the context and the environment at the Irish level, at a pan-Irish level, was very fragmented so far. We need a more unifying vision to develop a coherent strategic approach to the development of quantum technologies at an academic, at an industrial, and hopefully bridging the two sides of the spectrum. And this was lacking so far. The context and the environment at the Irish level was too territorial. The initiatives were too small to give evidence of the existence of a critical mass to coordinate large-scale initiatives. And hopefully the initiatives that have been put forward recently in the whole island, from Sequest to CUSEC to the engagement in North-South initiatives, will cure this syndrome in a sense. The engagement of the realities in the island dealing with quantum technologies with quantum technology related companies and industry has been ad hoc, has been personal, so to say. We need instead to develop an ecosystem that indeed underpins the efforts that as an island we want to push. Okay, so putting together North and South. Enhanced participation in opportunities for engagement. EuroQCI was mentioned a couple of times already this morning. The engagement of Ireland in EuroQCI was sort of thrilling. They missed, the country missed the opportunity to participate to this initiative and only very recently joined in. The return in terms of engagement with the quantum flagship initiatives or Quantera overall could have been stronger, could have been better as a country overall. And this includes also the involvement of my side of the UK in a sense to this, in terms of participation to these major initiatives. And this is what we should do to develop a coherent approach. So what is the roadmap? The roadmap, in my opinion, consists of 5 petals, okay, so 5 strands. Focus on research strength across the countries, across the island, attract talents and expand the portfolio of research strands that we can manage, lead and coordinate the effort, not only at a national level, but at an all-island level, build structural industrial engagement and partnering with European leaders in the area. In terms of research strength, there is a lot to take advantage of. From the development of and the analysis of quantum materials and nanostructures to quantum engineering infrastructures and quantum communication security, the integration of quantum devices, the engineering of quantum states from sources, and a strong theoretical compartment, theoretical unit for the development of quantum technologies. These are technological enablers. These are strengths that are already available in the whole island, and that these community needs to leverage upon to underpin the program for the development and the success that Ireland can have in the development of a quantum technology program. It needs, as an island, it needs to be the inertia that has been dragging us so far to make a rapid impact. We need to expand our initiatives, again, leveraging on the strength, focusing on the enablers that we have available, but also building on top of them to achieve new goals. And in this regard, some of the themes that have been addressed this morning are key, from quantum simulations to artificial intelligence for quantum problems, quantum communication infrastructures and the integration with classical frameworks. These are strengths that we can leverage upon right now, and the input coming from Sequest will be key in that. The coordination of the Irish effort is possible. There are plenty of opportunities around going across the border from south to north that leave a strong hope for building a multi-spoke center for excellence in quantum technology. Finally, the engagement with quantum industry should follow, in my opinion, the model of joint ventures a la German style, and to build and train new quantum engineers, a new generation of quantum engineers able to develop the current infrastructures. The engagement with European leaders should be proactive rather than reactive. We should make sure that our people get in touch with realities across Europe, and we should make sure that as an island we participate to initiatives like EuroQCI, but also EuroQCS, which is the analog of EuroQCI for quantum simulation. Okay, with that, I'm done. And I'm looking forward to add more pins to this map to see a genuinely pan-Irish effort in this exciting field. Welcome, Sequest, and thank you so much.
And thank you, Mara, for that fascinating presentation. And again, showing all those pins around the map, how much of an all-out perspective this really is. Now, we're about to get to the messages from the heads of the schools. But before we do that, a reminder to all of you that very shortly, Andrew's going to be coming back up here with me to answer your questions. So it's your last chance to get them in is during this next little segment. So we know some of them have been answered already during the chat, but get your questions in and Andrew and I will be here to answer them, but I'll be here to ask them and Andrew will make me sound very smart. But now we get on to the messages from the heads of the schools, because it is a collaborative effort with the School of Physics, the School of Mathematics and Statistics, the School of Computer Science, and the School of Electrical and Electronic Engineering.
Good afternoon. My name is Emma Sokol and I'm the incoming Head of School of Physics. And I'm delighted to be involved with the Sequest launch. I'm just sorry that we can't be all together in person. The involvement of UCD in quantum science can be traced all the way back to the end of the 19th century, when Thomas Preston, who was a professor of natural philosophy at UCD, built magnets, and he used these magnets to discover the anomalous Zeeman effect. Unfortunately, Thomas Preston died very young, and many feel that this prevented his significant contribution to quantum science from being properly acknowledged. He did, however, win the Boyle Medal. In the present day, the School of Physics and its alumni support PhD scholarships in fundamental physics that are named for Thomas Preston. So we're keen to keep our association with quantum physics alive. And in the present, the research profile of the school has significant emphasis on quantum physics, based both theoretically with condensed matter theory and quantum thermodynamics, and experimentally with research groups in particle physics and atomic molecular and plasma physics. Connections between these groups are not always immediately obvious, but for example, atomic and molecular collision physics, which is part of my research profile, is directly relatable to the realization of a quantum computer. And people studying the trapping and behavior of ions frequently relate this behavior and this science to the realization of an actual quantum computer. Furthermore, quantum physics forms a pillar of our undergraduate programs, and we have quantum physics modules in all 4 years of our programs. And Sequest represents a fantastic opportunity to bridge the gap between this fundamental physics education in quantum physics with quantum science and other disciplines. And furthermore, it represents a platform to introduce our students to developments at the very forefront of quantum technology and allow them to relate their knowledge to the research frontier. I'm very pleased to support the launch of Sequest and look forward to being involved personally and on behalf of the School of Physics in the exciting interdisciplinary opportunities that it will bring to the field of quantum technology. Thank you.
To develop the full potential of quantum technology, there are many difficult problems to solve. A key objective is to make multi-qubit systems and to connect them to existing computing and communications infrastructure. This presents many exciting challenges, especially in the field of electrical and electronic engineering. Therefore, as a school, we're delighted to be a founding partner of UCD's Quantum Centre. Members of our academic staff, including Professors Bogdan Stasevsky and Elena Blakina, are already international leaders in silicon-based quantum research and technology. This has the advantages of being compatible with existing microelectronic circuits and manufacturing processes. We will shortly be launching educational programs to train not just users of quantum computing, but the inventors who will engineer our quantum future. We wish the Centre and those involved in it every success in this great venture.
Quantum computing could break encryption, revolutionize communications and the simulation of molecular modeling. The study of information processing and transmission involving quantum computers introduces new and very exciting areas of mathematical research. These words are taken from our school webpage. They introduce the research group on quantum information and computing in the School of Mathematics and Statistics. Within the school, this research group is interested in things such as quantum information theory, quantum computing to solve classically intractable tasks, post-quantum cryptography to develop cryptographic systems that are secure against both quantum and classical computers. We recognize that quantum science is an essentially interdisciplinary subject. It involves theory, it involves experiment and technology. As a school, we look forward to playing our part in Sequest. We're delighted to be here at the launch of Sequest, and I wish this interdisciplinary centre every success in its endeavours going forward. Best wishes today from the School of Mathematics and Statistics.
I'm delighted that today marks the launch of the Sequest Research Centre. Quantum computing holds the potential to radically change the computing landscape. Highly computationally complex problems, which were once intractable, could well be solved routinely by quantum computers. This transformation could potentially revolutionize applications as diverse as cellular biology, cryptography, and materials science. While there is certainly great promise, there remain many challenges to overcome. Physicists, engineers, mathematicians, and computer scientists must forge new interdisciplinary collaborations to find novel solutions. Computer scientists must rethink the foundations of programming. We must invent new algorithms which exploit the power of quantum superposition. We must evolve new paradigms for software development in the post-quantum world. This is an exciting time. I very much look forward to seeing the research ideas and technological innovations which will be created by the Sequest Centre in the coming years. I am pleased to say that the Sequest Research Centre will lead UCD towards the future of quantum computing.
And welcome back, Andrew.
Thank you.
Great. Before I continue, I just want to thank all the heads of school there for your messages there. It's wonderful to have your support for Sequest. Andrew, we've been taking the questions down as they come in. Some have been answered in chat by some of our other speakers. We've got a few just for you now. And you're going to answer them with me live. So the first of these is about Sequest's ambitions with regards to the European Commission's quantum flagship program. So what are Sequest's ambitions in this regard?
Well, I mean, the EU quantum flagship is obviously a big enterprise, and it has a number of different goals. I mean, one of the main aspects of the flagship is to consolidate and expand the EU leadership and excellence in quantum, to kickstart a quantum industry, if you like, in the EU, make it an attractive place for innovation. I mean, all of these things are things that we want to do in Sequest, or at least facilitate that. We certainly want to develop the sort of quantum research area within Sequest and collaborate with companies to make this a sort of attractive place to do their work.
That's fantastic. And you mentioned sort of the collaboration with companies, and you mentioned earlier on about the lot of academic interest in the centre. But are there activities for the general public, say those who are more my background possibly, or those who are more amateur enthusiasts towards science and technology and engineering, for them to get involved with?
Well, part of the quantum literacy pillar that we heard earlier about, I mean, part of this is certainly to engage the public and do outreach and so on. And I think it's important that we have workshops, not just for students, but also a way of engaging the public. one way of doing this would be nice to have some public lectures. We actually have one already scheduled on the 26th of August. We have Klaus Smolner giving a public lecture. Anyone can join in on this. The registration can be done through the Quantum website. And so Klaus is a fantastic speaker. He's a really important person in the field. There's even a quantum gate named after him. This should be a really fascinating talk. This is open to everybody, be really accessible.
So just even a quantum gate named after him is like saying that so casually. He's like, that's a pretty big deal.
That's a pretty big deal.
He doesn't know. It's like it'd be up there like saying there's also a statue for me, for my achievements in the field of excellence. So we're looking at the current students here though, and the future students of UCD. I suppose what are the opportunities that Sequence is going to bring for them? I suppose both, not just in terms of research, but I suppose in terms of courses and everything beyond that.
I mean, as I mentioned earlier, I mean, we have a lot of researchers in Sequest in the different schools. They all have their own specialisms. They're all working away in their individual schools. One of the things we want to do with Sequest is really kind of try to bring this together. So one thing that we can do in terms of education for the students here in UCD is we'll have this so-called structural elective, which basically means that students can have on their degree certificate that they have a quantum concentration, if you like. They can take different modules in all 4 of our participating schools. So this is going to be a new thing. This is really exciting because it means that if you're doing a physics degree, you don't just have to take the quantum modules in physics, you can now also take some modules perhaps in computer science or engineering, but still with this quantum flavor. I think also because we're launching this centre, we've got this critical mass of different researchers. Obviously, there'll be a lot of different research projects available. So for sort of final year students who are doing their research projects, there'll be a lot of different options for them to pursue. So hopefully, there'll be a lot of opportunities for our current and future students in the quantum arena.
And just on that, because you mentioned that example of the physics student, or maybe doing something engineering, or engineering doing something like computing. Like that ability, that cross, disciplinary research, because that's so critical to what UCD as a whole is doing right now. To see this happening here for you, it's been a big adventure for you, Andrew, isn't it?
Yeah, absolutely. I mean, it's really about this joint effort, if you like, and this is something we want to pass to the students as well.
That's fantastic. Well, thanks, Andrew, for joining us at the beginning of our journey. Thank to all our speakers today. Most of all, though, thanks to you who joined us throughout this. There's a few other people I have to say a quick word about, though. They are Dr. Steve Campbell, Dr. Kevin Murphy, and Katrina O'Leary, as well as all the team who you largely didn't see on screen. Steve was on screen, so he gets a double thank you, really, because they did so much work to make sure that Andrew, me, and everything else you saw worked smoothly without any problems. So thanks to all of them for their help today. You can learn a lot more about what's going on here with Sequest. This is the beginning of the journey, like Andrew just said there, at ucd.ie/quantum. And if you didn't catch the start of this or you missed a couple of bits, don't worry, all of it is on the Sequest YouTube very shortly. Or if you're already watching it on YouTube, you already know that, and I just told you what you're already doing. But until next time, thank you all very much for joining us. I've been Emma Bryan from Connected, and this is the launch of Sequest.